implementation, ASIC implementation. Say, for example, I want to implement a router. The router implementation, it's a complex circuit for internet connectivity. So I may go for a router implementation. So that is a relatively simpler one when compared with a mobile phone. So I need to choose. Why this discussion is, yet a system generator, I need to choose. Yeah, so I need to choose the appropriate FPGA. So I need to click on system generator. If I double click the system generator block, I get the option of, okay, I'll get the option of choosing the appropriate FPGA which I have listed. So you need to choose, suppose you have purchased a particular FPGA, field programmable gate array. So you need to choose that particular FPGA as your system generator need to be configured as that particular FPGA. So now, yeah, so now what I will do is I will show you on this tab, I will show you the system generator. Just I will show you the system generator properties that you may change. So here, just I'm highlighting the system generator. This is what, if I double click this system generator toolbox, yeah, this is what I told you, Simulink start page. You can browse the, are you able to see the Simulink start page? You have a digital filter, feedback controller, some examples are there, blank library, digital filter, code generation block, feedback control. So you have built-in blocks and you have block sets like aerospace block set, DSP system toolbox block set, HDL coder. So DSP system basic filter block set, mixed signal system, and yeah, you have HDL coder block set. Under HDL device under test, MATLAB arithmetic blocks. Okay, you have register blocks, Simulink hardware, serial FIR, like that, state machine implementation. So I may just choose these blocks. So why this discussion is, if I want to draw the binary amplitude shift keying block diagram, I need to open my Simulink, and from the library I have to choose this sine wave, pulse generator, and all those. If I double click on system generator, you observe here, I have an option of choosing appropriate hardware FPGA board. Can you see the list on the screen? First one is being Kintex Alpha Ultra 96. Is it visible on the screen?
Yes, sir, we can see the screen, sir.
Option of that board, okay, Arctic 7, Kintex. So what are all these? Wide variety of FPGA boards that are available. So for I want to choose a latest, so I procured a latest FPGA board on which I want to implement my digital modulation scheme. So let me select that FPGA board. That's it. See, my intention of this is, I am not aware of the hardware description language, its syntax, nothing is me, but I want to implement a digital modulation scheme. The easy and simpler way is go for a block diagram level implementation. So the block diagram of a BASK is available with me. A pulse generator is required, a sine wave generator is required, and a multiplier. So these are my simple requirements. So just go to MATLAB, open a Simulink start page. from the Simulink library, I may browse for these blocks and just connect them appropriately. Then my block diagram implementation is over. The next step is, see whether this is producing my required, the functionality is correct or not. On the Simulink block diagram, this one, just double click on the scope. If I double click on the scope, what it does is it automatically a PSK waveform. So you can see this scope. It has generated the wave, okay, a PSK waveform. I think see on the screen the PSK waveform that got generated. So if I just double click, it automatically generates. If now the difficult part is that this the simulation of this one takes a little bit more time. So you should have a desktop or a laptop with higher RAM size, probably gives good speed of simulation. Okay, so this now output waveform is visible. Just I double clicked on that. Now the scope waveform get the output of the scope, which is the waveform viewer, gave me this out. Now up to that part it is fine. Now the just the scope gave me I got my required BASK output waveform. That's it. But target, I want to program FPGA start behavior as a ASK, amplitude shift ASK. And for that sake, is I should put a system generator block, but a system generator. This is X corresponds to Xilinx system generator block that links the Simulink and the FPGA, that links the hardware description language. It creates this system generator tool, the HDL for me, this system generator. So you choose appropriate FPGA board here, and you have in this compilation you have IP catalog, hardware netlist. What is HDL netlist? Is hardware description language netlist. This what is this netlist is? I should get a netlist, okay, with which again I can create a to program my FPGA. That is what the netlist. And the hardware software co-simulation gives me the advantage of straight away programming my FPGA board like Z board. And the hardware description language, as I told you, just click on hardware description language menu. What you can see on the screen, you can see VHDL and Verilog. And now I have highlighted VHDL because I am comfortable with VHDL netlist. If I am much comfortable with Verilog, just let me choose Verilog. It gives you a good clarity of what is to be chosen. If you have comfort with VHDL, just choose VHDL. And if you have comfort with Verilog, then choose the hardware description language called Verilog. And whatever the netlist that get created, you are showing here a target directory. So the target directory is netlist, and the strategy is there. So Vivado is the name of integrated development environment provided by Xilinx. Earlier, the Xilinx has given a integrated development environment with the name Xilinx ISC. Most of you might be aware of this ISC, integrated simulation environment or software environment, and we already discussed what it consists of. Is a text editor, compiler, compiler, debugger, and linker. So all these Xilinx ISC consists of a then synthesizer, then translating is a step, translating, mapping, placement, and routing. So these are the steps FPGA design cycle. So the FPGA design cycle consists of simulation that gives a functional verification. Functional verification means, just now we have seen the functional verification of amplitude shift key. That is nothing but we got the waveforms. That is what the functional verification. Now, simple verification is, I want to do the functional verification of an AND gate. What should I do? I should provide a set of input test vectors, input 0, 0, 1, 1, 0, 1, 1, and I should get appropriately for all the 0, 0, 0, 1, 1, 0, I should get a 0, and for 1, 1, I should get a 1. So that is what the functional verification. Simple. That is called simulation. Simple. Simulation is nothing but the functional. Behavioral simulation is simple functionality verification. And now you got the clarity of by simulation. Synthesizer. Synthesizer is nothing but netlist understandable by your hardware. It creates an understandable netlist, the synthesis. And after synthesis, there is a step called translation. There is a step, translation, mapping, placement, and routing. So what is meant by placement is, your blocks need to be placed. So a particular block which require power supply, VDD, is to be placed nearer to VDD. A block which requires the ground is to be placed nearer to the ground. And then a bit which require power supply is to be connected to the power supply with a connecting wire, and that is called routing. That's it. So I need not worry about, I am not aware of these steps. These are very simple steps that are design cycle. Again, once again, I'm manipulation, synthesis, translation, mapping, placing and placement and routing, and finally a dot bit file from file generation, programmable memory generation, from dot bit file generation, hex file generation, with which I will program my FPGA. Now you choose just the system generator properties. You have chosen appropriate properties. And Vivado, we are here, Vivado synthesis default. Yeah, you may choose flow area optimized high, flow area optimized medium. So you have wide variety of, so I may even choose the synthesis strategy. I want to optimize the, I want to optimize DSP. Okay, routability, I want to optimize the routing. Okay, so I have the tool itself is this thing. See, why do we go for VLSI implementation? Three major advantages. Delay gets optimized, okay, and the area gets optimized, okay, power gets optimized. So I may target for all the three parameters, okay, but simultaneously achieving all the three is difficult because power P is equal to CV square F. Power is directly proportional to the frequency of operation. If I want to operate my design at higher speed, power consumption will be high. So that means I should have lowest delay for my circuit. So I need to compromise on power. So the process, the implementation consumes more power. But I may get the optimization of the area. Okay, so because I am compromising on power, the other two parameters like the area and and the delay can be optimized. So that is what about the optimization and the implementation strategy. Now you may say apply, click on generate. So as a result, you observe that a netlist wherever your wherever your design got located, you will get a folder called netlist. I think on the screen you are able to see a folder called netlist. So just double click that netlist. And is you observe bit file amplitude shift key underscore dot bit file got generated. It is a programmable dot bit file that got generated. Now in a similar manner, now you go TL underscore netlist. So hardware description language netlist, and here you will of a ASSG, that is a project file. So you got though of the hardware description language, you got equivalent HDL. Click that ASKSG project. I get this is nothing but a Xilinx IDE. Xilinx is the name. I got a Xilinx IDE environment where I can see my ASK or SG corresponds to say system generator. So I this you may observe. Have I written the code? No. K underscore SG dot BHD code got generated with the name of the P as ASK and its inputs. You observe gateway underscore in and gateway underscore into. These are the inputs. Port, PORT, these are the keywords. Entity is nothing but, suppose I want to design a AND gate. Name of the entity is AND gate. Is, I will write is. Then port. I will give my list of inputs. And I require a clock. It is an input. The output is gateway underscore output. Standard logic vector. The size of my output is 0 down to 21 minus 1. So that means I got I have given an array of output array of size say 22 and end this particular entity name and architecture. Inside my this one I require a multiplier. So mult underscore P, one of my signal. And gateway. So I got a dot VHD, means a VHDL equivalent VHDL code got generated. Have I written this code? No, I have not written the code. This is what the advantage of a system generator tool that is available. So there is a linkage between the MATLAB environment and your Xilinx environment. So I can create a synthesizable HDL netlist. making use of the MATLAB Simulink environment. So this is an easy way of generating the required digital modulation scheme just with the knowledge of the block diagram level entry. Say with simple block diagram level entry, I'll be able to generate a programmable file with which I can program my field programmable gate array. Now, so if you go for hardware, software co-simulation, you have settings for hardware, software co-simulation. So if I click on this hardware, software co-simulation, it automatically generates a line called a generator block called gateway into is in inputs gateway into, and other input is gateway in and JTAG, okay, joint test, okay, JTAG, and co-sim, that means hardware software co-simulation, and gateway out. Now this block is to be taken into what? Into your Simulink environment. Now into the Simulink environment, you have to insert this block. Okay, you have to insert this, which block? The library block, a JTAG co-sim block that got generated. Now the question is, why should I include this? ASK underscore SG hardware software co-sim. So hardware software co-sim block. This enable me to straight away program my FPGA. What I can do is just I can connect my FPGA hardware kit to my desktop or laptop with a connecting wire. So automatically the vendor, FPGA board vendor, what he does is he will provide me a USB cable. That itself is a power cable and the data connecting cable. That with which I can program my hardware FPGA board. Okay, that's it. So now it is as simple as just connecting with a USB cable my FPGA board, and I can program my FPGA. Now after programming my FPGA, now my FPGA FPGA chip will start behaving like a amplitude shift keying ASK modulator, amplitude shift keying block. That's it. So simple to do this one. I think up to this, is it clear for everyone, or do you have any queries related to this implementation? See, with one go, it may not be coming. You require a little bit of practice. Okay. So with one go, it may be a little bit tough, but if you practice, this becomes easy. So I am giving you a very easy and simple way of implementing without learning the hardware description language. I may simply go ahead with a block diagram level entry. Just click Simulink and open the Simulink block set library, and then connect all the required blocks like sine wave generator, pulse generator, gateway in and out blocks, and you require a type casting, you require a converter from float to fix, and then give it to a multiplier block. Output of the multiplier block is connected here and give it to a scope and verify the functionality. Now, in the presentation, in the PPT, you may observe two block diagrams. This block diagram is a simple Simulink block diagram without including the system generator block. Can you identify the difference between this block diagram and the next one? The slide, it is shown here, and the slide that was shown here. The variation is here you have included additionally this system generator block. We must include this system generator block in order to program any target FPGA. So that is what our requirement is. Okay. Now, this is the PSK Simulink waveforms. So with the Simulink tool we have generated, and now we may go for PSK generation using Simulink binary frequency shift key. Again, very important is block diagram. What is the variation that you observe for the ASK modulation block diagram and this block diagram? What is the variation that you got? Yes? What is the difference you got? If you observe the two block diagrams, there in the ASK you have a sinusoidal carrier. A sinusoidal carrier is there. Another block is a pulse. Am I right? Pulse generator block. Can you observe? Whereas when it comes to your BFSK generation, you observe two sinusoidal generators are there. Can you observe that? I'm highlighting this. Two sinusoidal generator blocks, and there is a switch S1, and there is a binary data message is there, and this is what your BFSK output. Now, keeping this block diagram for BFSK modulation in mind, we need to go for the implementation of this. So how do I implement? Observe what I did. I from the Simulink library, I have added one sine wave, right? One sine wave generator. Another sine wave generator I could add. And there is a pulse generator block. Now all these are given to a switch. Observe, this is the switch. So and clearly here it is written switch. And finally, the outputs are given to this one and then scope. That's it. Simple. Now the design is over. Observe that what is missing here, there is no system generator block in this BFSK block diagram. And this is the BFSK block diagram by adding this system generator. As I told you, what is the need for this adding this system generator block? This system generator block will enable me to create a programmable file for programming my hardware, for programming my FPGA. Okay, this is creating me a programmable read-only memory PROM file gets generated with this system generator. A HDL netlist gets created. Okay, so I have browsed sine wave and a pulse generator with double output is taken, and there are 3 gateways to provide inputs and outputs, connectivity between my sine wave generator and this one. And observe that 2 converters are being used because we discussed clearly. We require conversion from floating point to this fixed point, and then these got connected to your multiplexer. So what is a multiplexer? MUX. Can you read this MUX? Just I have highlighted. Multiplexer is a selection one. So it converts many to one. That means I have three inputs. Out of three inputs, one of the inputs is chosen as the output based on the selection. So there will be a select line. On the select line, so my D naught, one of the input is D naught, another input is D1. Out of D naught and D1, one will be chosen as the output based on the selection line. Selection line can be 0 or selection line can be 1. When selection line is 0, I will write the code. If select line is 0, okay. If selection line is 1, one of my input D1 gets selected, and that will be my output, and that will be my output for this multiplexer. And this is given to the gateway out, and the output of this is given to the scope. And just if I double click on this scope, I get this PSK waveform. You can see a square waveform, you can see a sinusoidal waveform with a particular frequency. Again, another sinusoidal waveform. Why? Because I am giving two sinusoidal wave generators. Can you observe here? Sine wave and sine wave 1. As a result, I got two sine waves here. One is here, another one sine wave here. So it got justified, and finally my binary frequency shifted key waveform, BFSK waveform. And actually on the scope you will get the waveform like this on a black background with yellow color. For the visibility sake, you can just use some option like invert color. The black background get inverted into a white background like this, and the waveforms gets highlighted. So the visibility will be good. So when we are doing project, and in the project report especially, when I take a print of this, this may not get proper. Okay, and instead of that, just your background, and you may get a clear clarity, visibility of the waveforms. Okay, now another important method is your PSK, phase shift keying. So we may quickly go to BPSK. So your signals are like this, and now I'm not explaining about BPSK. I am explaining based on the block diagram how to generate a BPSK. Okay, so I am not going in detail about the binary phase shift keying, because you are already aware of these all the digital modulation techniques. Just I am going ahead with the generation part and generating them, and particularly the VLSI implementation. So you got two sinusoidal carriers. One is a sinusoidal carrier with 0 degrees phase. Another one is a sinusoidal carrier with 180 degrees, and you have a switch for selection of these waveforms, and the binary data or the message signal is given through a pulse generator, and the switch S1 selects among these whichever get connected, that will get chosen, and this particular BPSK block diagram, generalized block diagram is shown, and based on this, now I will open my Simulink window. Okay, so MATLAB, in the MATLAB environment, option is there for me to open my Simulink. In the MATLAB environment, click on Simulink. If I click on Simulink, it will open the start page. Now, as I have already, just I will open this file. Go to open, and it will ask me to choose where my file got located. So I have done in a folder. So now what we are discussing is about the VLSI implementation of BPSK. So I have to choose this particular BPSK. So BPSK. Now this will open me the BPSK waveform. So here I will get BPSK SG. So so I have drawn this. Actually, already I have drawn in the interest of time. Okay, if I go on drawing this, it takes more time, right, for drawing all the digital modulation techniques. So for your convenience, I have pre-drawn all these modulation techniques. They were drawn, but if you start doing it, how many blocks are there? Yeah. So what happened now? What happened? The BPSK simulink block got opened. So if I click on scope, double click on this, so it automatically generates my required. Okay, so yeah, can you observe? Now this is what the waveform window got opened. Can you observe? Just by clicking on the scope. So in the scope, the waveforms will be visible like this. Now what is missing here? What is missing in this one is system generator block. Now, why do I require system generator block? In order to program my FPGA, a programmable memory file is to be generated. For that, I have to link my MATLAB Simulink environment to a Xilinx ISC environment. So what should I do is, just I have to system generator block. So what I have to do is, I have to browse from my library and then add this one. So after adding that, system generator block, this is what my binary phase shift keying system after adding the system generator block. So after generating this system generator block, double click on this system generator block. Double click on this one. What it does is, it opens a window like this. Now choose the appropriate FPGA board. I may now just change for my convenience, so something like Spartan 3 or Vertex 7. We have already discussed wide varieties of FPGA boards are available. So whichever FPGA board is available with me, just what I will do is just click on that and choose my appropriate. Now observe that earlier it is ZED, Z board or Zinc board is one of the boards of FPGA. Now what it got changed? It got changed to Vertex 7, and now compilation is hardware co-simulation. Okay, and VHDL is the hardware description language, or I may choose Verilog. Just change to Verilog. Verilog file gets generated. Target directory, I may browse and choose appropriate target directory and click on apply. Click on generate. So if I do that, this will go on running. Observe what is happening on the screen. You got a window, and here you are getting an indication generating. That means it is generating a netlist file. So performing compilation and generation, compilation status. Can you see a window showing that performing and compilation and generation? So you get the compilation of this netlist file. So after that, you may just go to, after this is over, you may go to the netlist folder, HDL netlist. Okay. So you get the creation of a netlist file, then go to HDL_netlist. Here you will get your especially BPSK SG_XLS file, and the MATLAB implementation results are shown here. And you may go ahead with the differential phase shift keying, DPSK. So the block diagram is given here. Your message input data MK is shown here, and there is a logic circuit. There is a product modulator. You can observe a delay block with TB delay. Okay, to the product modulator, cos 2 pi FCT is one input, another input is DK, and a differential phase shift keyed signal, DPSK signal, is your output. So instead of operating with respect to a constant reference wave, the broadcast can operate with respect to itself. Changes in the phase of a single broadcast waveform can be considered as a significant item. In this system, the demodulator determines the changes in the phase of the received signal rather than the phase itself. Since this scheme depends on the difference between successive phases, it is termed as differential phase shift keying. You know about DPS. PSK can significantly simpler to implement than ordinary phase shift keying, since there is no need for the demodulator to have a copy of the reference signal to determine the exact phase of the received signal. But it has a drawback. It produces more erroneous demodulation. Information of DPSK is shown in this particular tabular form. And here is a Simulink block diagram for differential phase shift keying. So you require two sine wave generators, sine wave 1, and you have a pulse generator, you have an XOR gate, and a delay element. See how beautiful the Simulink toolbox is. Just you can select from the library the delay element, this Z inverse. Just like on the paper, you draw the block diagram in a similar manner in the programming environment. You can just drag and drop that block, connect those blocks, and get the required operation of that particular system. How beautiful the tool is. So you can appreciate that we have such a sophisticated Simulink tools and Simulink blocks are available in the environment. So though I am not a VLSI expert, I could comfortably generate my modulation schemes very easily. Now this is the DPSK with system generator block got included. Again, click on scope. So let us go back and see. If you remember, we have just generating generator we have to. So on generation, I told you that because of creating number of compatible HDL files, the process is definitely going to take some time. Okay, that is the reason why I have shown you. Observe on the screen compilation status. This is showing performing compilation and generation time. But though it takes more time, if I'm not a hardware description language expert, HDL expert, this is very easy for me. Though I don't know hardware description language, just with my block diagram level entry, I will be able to program my FPGA. That is what the advantage I get with this Simulink block and yeah, system generator. Now the figure shows the DPSK waveform obtained from Simulink simulation. Figure A is a square waveform. This is not properly adjusted. Just figure show again with the differentially encoded data is the second one, square waveform. Figure C, this shows a sine waveform, and a differential phase shift keyed waveform, DPSK waveform, is shown at the end. So yeah, with these implementation of few digital, even you can extend it for your implementation like QAM, quadrature amplitude modulation. Okay, QAM and other digital modulation techniques can also be implemented. And also even you can go to the extent of creating an entire communication system with the knowledge of with the knowledge of Simulink system generator tool. You can implement a communication system, and you program the FPGA as a simple communication system. That is also possible. Okay, so within the available time, I tried my level best to give you the overall view of how practically the MATLAB Simulink environment, system generator tool, and Xilinx Vivado are available to implement various digital modulation techniques. To the best of my ability, I tried. Okay, I think you got at least a delta X kind of